Good evening, everyone. Welcome to the week 8th of this tutorial session on this course of Principles of Modern CDMA MIMO OFDM Wireless Communication course. So today we will see some of the concepts based on MIMO and OFDM wireless communication, and also we will see some of the examples and questions based on these topics. So before coming to that, we'll solve a question based on singular value decomposition. So consider a 3 cross 3 MIMO channel. So 3 cross 3 MIMO channel means there is 3 transmitter at the base station and 3 receiver at the user side. So this is given as so this have 3 receiver, that is the number of row is 3, so 3 receiver and 3 transmitter based on the number of columns. So for singular value decomposition, we have to break this H in such a way that it is in the form of U covariance matrix and the V of Hermitian matrix. And the properties of U and V are like U Hermitian into U is the identity matrix, and V Hermitian V, that is equal to V into V Hermitian. This is also identity matrix. So how we are going to break, like as U Hermitian U is given as identity matrix, so first we'll take our channel vector, that is 230 minus 640 002. So we will normalize the each column. So we'll get h is equal to 2 by under root of 13, 3 by under root of 13, 0, minus 6 by under root of 36 plus 16, that is 52, 4 by under root of 52, 0, 0, 0, and 2 by under root of 4, that is equal to 1. Now after normalizing, we will multiply with the factors to the each column, so the multiplication will become again same to the H matrix. So we'll multiply the second column, like element of second column of U matrix, by 52, . and third column by 2. So here, and also we have to keep in mind that singular values should be in the decreasing order. So here the singular values are not in decreasing order. Like it should be root 52 is greater than root 13, and that is greater than 2. So for making in the decreasing order, first we will write here root will interchange the both the row 1 and row 2 of this, so it will become 0 root 52 0 root 13 0 0 and 0 0 2. And here we can write it as, we will interchange the column 2 with the column 1, so it will become minus 6 by root 52, 4 by root 52, 0, 2 by root 13, 3 by root 13, 0 0 0 1. Now we can do one more thing, like we can now interchange the row 2 with row 1 of this V matrix. So we'll get root 52 0 0 0 root 13 0 0 0 2, and here we'll multiply with an identity matrix by changing the column row 2 with row 1, so it will become 0 1 0 1 0 0 and 0 0 1. So this is a singular value decomposition of the channel matrix. So here this term is VH, V Hermitian, this term is sigma, and this term is U. And U Hermitian U will be I, V Hermitian V is equal to V into V Hermitian will be I, and the covariance matrix is root 52 0 0 0 root 13 0 0 0 2. So here the singular values are root under 52, root under 13 and 2. So sigma 1, sigma 2 comma sigma 3 is greater than 0, and also sigma 1 is greater than sigma 2 is greater than sigma 3, that is in decreasing order. Now at the receiver end, we have to get back the transmitted symbol. So estimated value of y will be y tilde is equal to u Hermitian. So our value is minus like this matrix we will take the transpose of this matrix because this is a real matrix. So it will become minus 6 by root 52 4 by root 52, 0, 2 by root 13, 3 by root 13, 0, 0, 0, 1. So this is our y bar. Now at the transmitter, x bar is equal to v x tilde. So this is given as x1, x2, x3. Our v vector is 0, 1, 0, 1, 0, 0, 0, 0, 1 as we have found before. And this is x1 tilde, x2 tilde and x3 tilde. So this is the transmit, like pre-processing before the transmitting the symbol. And the received symbol can be given as y bar sigma x tilde plus w tilde. So this is y1 tilde, y2 tilde and y3 tilde is given as the this is a singular value matrix, that is root 52, 0, 0, 0, root 13, 0 and 0, 0, 1. Plus the noise, that is w1 tilde, w2 tilde and w3 tilde. So this we can break also, that will be root 52 x1 plus w1 tilde and y2 will be root 13 x2 plus w2 tilde and y3 will be 2x3 tilde plus w3 tilde. So this is the three channels that is forming the spatial multiplexing. Now we will see the concepts of optimal MIMO capacity. So capacity is basically given as log 2 1 plus SNR. So in the case of MIMO, the capacity Ci will be given as log 2 1 plus So total capacity C will be summation of log 2 T is equal to, sorry, I is equal to 1 to T 1 plus Pi sigma I square by sigma n square. So now we have to maximize this. So the optimal MIMO capacity problem can be given as the optimal MIMO power allocation can be formulated as, like, we have to maximize this term, the capacity what we have written above, that is log 2 1 plus Pi sigma I square divided by sigma square, and this is subjected to the constraint. The constraint is given that summation of all the Pi should be less than P. So now we will use the constraint optimization problem by using Lagrange multipliers. So we can write the Lagrangian cost function can be written as here function of P bar and lambda. So this is given as I is equal to 1 to T plus lambda P minus summation of Pi. So now to optimize this, we have to, as summation of Pi is less than P, so P minus this term will be always greater than equal to 0. So to optimize this, we have to do the derivative of this function, Lagrangian cost function, with respect to Pi should be equal to 0. So now when we do the derivative with respect to the Pi, we will get So the value of lambda will be minus of no, because it's minus lambda, so lambda will be sigma I square by sigma square divided by 1 plus pi sigma I square by sigma square. So 1 by lambda is equal to 1 plus 1 by lambda will be sigma square by sigma I square plus pi. So from here we can get pi is equal to 1 by lambda minus sigma square by sigma I square. So we can write pi is equal to this only when this term is greater than 0. If 1 by lambda minus sigma square by sigma I square is greater than 0 and 0 otherwise. So now we'll solve a question based on this. Consider the MIMO channel matrix H given as considering a transmit power of P is equal to minus 1.25 dB and noise power sigma square is equal to 3 dB. Compute the MIMO capacity and optimal power allocation. So in this question, a channel matrix H is given, and we have to and also the transmit power P is given minus 1.25 dB and the noise power is given as 3 dB. We have to compute the MIMO capacity and the optimal power allocation. So we have studied all the concepts based on this. So we'll solve this question now. Like in this question, 3 cross 3 MIMO system is given with number of receive antenna is equal to number of transmit antenna, that is given as 3, and the noise power is given as 3 dB. So that is equal to 10 log 10 noise power is equal to 3 dB. So we will get 10 to the power of 0.3. So this is equal to 2, and the power is given as minus 1.25 dB. So 10 log 10 P is equal to minus 1.25. This implies that P is equal to 10 to the power of 0.125. So that is equal to 0.75. Now we can observe that here C1 and C2, C1H into C2 is can be given as 2 into minus 6 plus 3 into 4 and plus 0 into 0. So this will equal to 0. And this is the same matrix what we have taken previously. So we will like we already found the singular value decomposition of this. So we will directly write, will not find it again because we have already found. So we can write H as this is our U. Singular value matrix will be this, and this is given as sigma, and the matrix B is 0 1 0 1 0 0 0 0 1. So here thus the singular value sigma 1, sigma 2 and sigma 3 for the above channel matrix is given as sigma 1 is equal to root square 52, is imply that sigma 1 square is equal to 52. Similarly, sigma 2 is equal to root under 13 and sigma 3 is equal to 2. So this is equal to 13 and sigma 3 square is equal to 4. So it can be seen that channel matrix H has 3 non-zero signal values. So it have 3 non-zero singular values. So the matrix of H will the rank of matrix H will be 3, and thus the channel capacity in terms of P1, P2, P3 is assigned to the different channel singular modes is given as, like, the channel capacity is given as C is equal to log 2 1 plus P1 sigma 1 square sigma n square plus log 2 1 plus P2 sigma 2 square by sigma n square plus log 2 1 plus P3 sigma 3 square by sigma n square. Now the above expression for capacity has to be maximized for the total power. So the total power is given as is equal to 0.75. So P1 plus P2 plus P3 is equal to 0.75, and also the total power formula what we have studied here is this: 1 by lambda sigma square by sig. So here our P1 is equal to 1 by lambda minus 1 by 26 plus P2 is equal to 1 by lambda minus 2 by 13 plus 1 by lambda minus 1 by 2. So here we can use this formula: 1 by lambda minus sigma square by sigma I square. And what is the value of sigma? So it will be 2 by 52. So it will be 1 by 26 and 2 by 13, and then 2 by 4, that is 1 by 2. So now this sum we have, this sum should be equal to 0.75. So when we do like this, will become 3 by lambda is equal to 0.75 plus 0. Plus 1 by 2 plus 2 by 13 plus 1 by 26. So 1 by lambda is equal to 0.75 plus 1 by 2 plus 2 by 13 plus 1 by 26 divided by 3. So 1 by lambda is equal to 0.48. Now the power allocation of the third channel P3 is equal to 1 by lambda minus 1 by 2. So that is equal to 0.48 minus 0.5. So this is equal to minus 0.02. So this is less than 0. So power 3 is coming out negative here. So it is not a possible allocation. So in that case, like we will take 0 power allocated for the mode 3 in the optimal location, and we will set n is equal to 2 and 0 power is allocated to mode 3. So now the total power P1 plus P2 will be given as, and the summation will be 0.75. So this time we will get 2 by lambda is equal to 0.75 plus 2 by 13 plus 1 by 26. It implies that lambda is equal to divided by 2. So sorry, 1 by lambda is equal to 0.4712. So now P1 is equal to 1 by lambda minus 1 by 26. This is also greater than 0. And P2 1 by lambda minus 2 by 13, that is also greater than equal to 0. So the value of P1 is equal to, when we calculate, we'll get 0.4327. And now this we can calculate in dB. So we will get in dB is minus 3.63 dB. And value of P2 is equal to 0.3174. So that is equal to around minus 4.98 dB. And P3 is equal to 0. So our channel capacity is equal to log to 1 plus we'll use the same formula. P1 sigma 1 square by sigma n square. So P1 sigma 1 square by sigma n square plus log 2 1 plus P2 sigma 2 square by sigma n square. So C is equal to log 2 1 plus P1 is 52. Sorry, sigma 1 square is 52. So we'll write it second. So P1 is our 0.4327 into 52. Sigma n square is 2 plus log 2 1 plus value of P2 is 0.3174 and sigma 2 square is 13. So when we calculate this value, you will get 5.23 bits per second per hertz. So this is the capacity, and unit is bits per second per hertz. So this, in this way we can find the capacity and the optimal power allocation, P1 and P2 and the capacity C. So now we will move on to the some of the questions, basics questions. The question number 1 is, as consider a bandwidth B is equal to 10 megahertz and number of subcarriers N is equal to 1024 in an OFDM system. The OFDM symbol time without cyclic prefix approximately given as. So here N is equal to 1024. So the OFDM symbol time TS, the symbol time is given as N by B. So that is equal to 1024 into 10 megahertz. Here B is equal to 10 megahertz. So this is equal to 10 into 10 to the power of 6. So after calculating, we will get 102.4 microsecond. So the correct answer is option number C. Now consider OFDM system with channel taps H0 is equal to 1 plus 2J, H1 is equal to 2 minus J in a system with N is equal to 4 subcarriers. The coefficient H3 for subcarrier K is equal to 3 is. So this is given as H0 plus H1 e to the power of minus J 2 pi 3 by 4. So this value will be 1 plus 2J plus 2 minus J and e to the power minus J 2 pi 3 by 4 will be like 3 pi by 2. It is 270 degree. So it will become minus it will become J plus J. So our H3 will be 1 plus 2J plus 2J minus 1. Sorry, plus 1. It will become 2 plus 4J. So the correct answer is option number D. The third question, Consider an OFDM system with noise power sigma square is equal to minus 3 dB. So 10 log 10 sigma square is equal to minus 3. So sigma square is equal to 10 to the power of minus 0.3. So this will become 1 by 2. Number of channel taps L is equal to 16. Number of subcarriers is 1024. And the transmit power P is equal to 30 dB. So we can write 10 log 10 P is equal to 30. So P is equal to 10 to the power of 3. So it will become 1000. And the if each channel tap is IID relay with average power 3. So the average power of each channel tap is given as 3. What is the approximate average output SNR at the receiver for each subcarrier? So the average output SNR will be expectation of HK square into P by noise power into N. So here first we have to find expectation of this term. So this will be summation I is equal to 0 to L minus 1 E of the each channel tap. So and also it is given the expectation of channel tap is 3. So it will become summation I is equal to 0 to L minus 1 3. So this will become 3L. So our output SNR will be 3L into P divided by N into sigma square. So now we'll substitute all the value and find the answer. So average output SNR, that is equal to 3LP N sigma square. So we'll substitute the value. So 3L is here 16, P is 1000 divided by 1024, sigma square is half. So after this we will get so we will get 375 by 4. So that will be around 93.75. So 10 log 10 93.75 is equal to 10 into 1.97 dB. So that is 19.7 dB is the correct answer. So option A is the correct answer for this question. Now coming to the question number 4. Consider a zero padded OFDM system in which the cyclic prefix is replaced by zeros. The frequency selective channel has channel taps H0, H1, H2, H3. Let the number of subcarriers be N and the zero padding of length 5. The output symbol Y1 corresponding to the output at time instant 1 for a noiseless scenario is given as. So the output Y1 is given as H0 X1 plus h1 x naught plus h2 into 0 plus h3 into 0. So this is given as h naught x1 plus h1 x naught. So the correct answer is option number C. Next question, what is the approximate data rate of LTE? So this is 100 to 200 megabits per second. So option D is the correct answer. Now, which operation is employed in the receiver of the OFDM wireless system? In the receiver, the fast Fourier transform or the discrete Fourier transform is applied. So option A is correct. So this is applied on the receiver, and inverse fast Fourier transform is applied on the transmitter end. Now coming to question number 7, consider a bandwidth B is equal to 10 megahertz. So this is given as 10 into 10 to the power of 6 hertz with a number of subcarriers n is equal to 1024 in an OFDM system. Let the cyclic prefix contain 256 samples. The OFDM symbol time with cyclic prefix is approximately given as. So the sample time, the symbol time is given as 1 by B. Total number of samples including cyclic prefix is given as, here, that is the total number of subcarrier plus total number of the cyclic prefix, that is 256 plus 1024. So this will become 1280. So the total OFDM symbol time with cyclic prefix is given as, like, total number of sample divided by B. So total number of sample is 1280 into 10 into 10 to the power of 6 second. So this will become 128 microsecond. So option B is the correct answer for this question. Now OFDM is used in which of the following wireless standards? So OFDM is used in WiMAX. Coming to the question number 9, consider total transmit power is equal to 3 dB. So we can write 10 log 10 of P is equal to 3. So P is equal to 10 to the power of 0.3. So it will become 2. Noise power sigma square is also given as 3 dB. So this will also become sigma square is equal to 10 to the power of 0.3, that is equal to 2. Now the singular values are given. Sigma 1 is equal to 1 by root 2 and sigma 2 is equal to 1 by 2. The optimal power values for the two singular modes are. So we have already studied that optimal power value is 1 by lambda minus sigma square by sigma 1 square, and for P2 it will be 1 by lambda minus sigma square by sigma 2 square. So P1 is equal to 1 by lambda minus sigma square is given as 3, and sigma 1 square will be 1 by 2. So it is equal to 1 by lambda minus 6, and P2 is equal to 1 by lambda minus 3 divided by 1 by 4. So it is equal to 1 by lambda, sorry, sigma is 2, because we have to take the normal value, not the value in the dB. So sigma square is 2. So this will become 1 by lambda minus 4, and this will become 1 by lambda minus 8. Now P1 plus P2 total power is given as 2. So this will become 2, is imply that P1 is 1 by lambda minus 4 and P2 is 1 by lambda minus 8. So 2 by lambda is equal to 2 plus 4 plus 8. So 1 by lambda is equal to 14 by 2, that is 7. So now our P1 is 1 by lambda minus 4, that is equal to 7 minus 4, that is equal to 3, and P2 is 1 by lambda minus 8, that is equal to 7 minus 8, that is equal to minus 1. So this P2 is less than 0, is imply that P2 is equal to 0, and then therefore P1 is equal to 2, as P2 is 0 and P1 plus P2 is equal to 2. So the correct answer is 2 comma 0. So option A is the correct answer for this question. Now consider a OFDM system with channel tap H0 is equal to 2 minus J, H1 is equal to minus 1 plus 2J, N is equal to 4 subcarrier. The coefficient H1 with subcarrier K is equal to 1 is given as H1 is equal to H0 plus H1 e to the power of minus J pi by 2. So this we can write as 2 minus J plus H1 is minus 1 plus 2J, that is e to the power minus J pi by 2 will be minus J. So this can be given as 2 minus J plus J minus 2J square. So that is equal to plus 2. So that is equal to 4. So the correct answer is option number B. So today we will stop the lecture here only, and this video is recorded and this will be uploaded on the YouTube, and link will be shared in the NPTEL portal. So thank you everyone for attending. So we can end the lecture now.